Hi everyone, welcome back to Chem Help ASAP. Now that we are experts at drawing our Lewis structure, this begs the question, what do we use it for? Well, one of the main things we use Lewis structure for is to predict molecular geometry. It's all very well to draw these Lewis structures on paper. That's only 2D. These are molecules in 3D space. So let's find out what they actually look like. The name of the model we use is called the Valence Shell Electron Pair Repulsion Model, or VSEPR model. And it is used to predict the 3D shape of molecules. And it does this by maximizing the space between electron pairs and also by recognizing that lone pairs will require more space than bonding pairs. Let's do methane as an example. There's the molecular formula. Here is the Lewis structure for methane. If you want to know how I got this Lewis structure, please check out my other video on Lewis structures. Now, is this drawing an accurate representation of the model in 3D space? Our drawing allows for 90 degrees in between hydrogen atoms, but if we actually move to 3D space, we can increase that to 109.5 degrees. Here is a 3D model of methane. I'm just going to rotate it a little bit so you can get an idea of how it moves in 3D space. See how much more space there is between the hydrogen atoms? You would have never thought on paper that we could get to 109.5 degrees between these, but once you switch over to 3D space, you see that obviously they have a lot more space than 90 degrees like we had on our paper. We can more accurately represent the 3D structure of methane on our 2D paper by using wedges and dashes. So I am going to redraw methane like so. The wedge here represents this hydrogen atom coming out of the plane of the paper, and the dashes here represent that hydrogen atom going behind the plane of the paper. The two lines for these hydrogen atoms represent those hydrogen atoms within the plane of the paper. In this drawing, it's a little bit easier to see that these bond angles are actually not 90 degrees, but they are greater than 90 degrees. Now, it is not practical to have a 3D model for every molecule, although we will see some more 3D models in this video. So we use a table to help us predict 3D shapes, and we use drawings to help us visualize those shapes on 2D paper. On this page here is my table based on the VSEPR model. Now, once we have drawn a Lewis structure for a molecule, we use the number of atoms bonded to the central atoms, the number of non-bonding, or these are also called lone pairs. And both of these things help us predict the shape of the molecule. Let's look at water. And let's get the Lewis structure for water. This drawing looks like there should be 180 degrees between these two hydrogen atoms, right? But the 3D model actually looks like this. Water's shape is actually bent. The lone pairs on the oxygen force the two hydrogen atoms closer to each other. Their angle is actually less than methane. It is 104.5. Could we have predicted that bent shape based on our Lewis structure? Yes, we can. We just need to look at our table on our other page here. I am going to rewrite the Lewis structure up at the top of the page just so we have it for reference. Now, using my table, I see that I have two atoms bonded to my central atom, and I have two lone pairs. So on my table right here, I can see two atoms bonded to the central atom, two non-bonding or lone pairs, and you can see the shape predicted here is bent. Now this table includes pictures to help you visualize in 3D space, where these yellow circles here are actually lone pairs, and the white spheres down here are your hydrogen atoms. But let's see what happens when we have double bonds to deal with. Let's look at the Lewis structure for formaldehyde. Carbon is the central atom. It's double bonded to oxygen with two hydrogens also bonded. It looks like an upside down T. What does our VSEPR table predict? Here is our table, and I have redrawn the Lewis structure just for reference. You can see that we have 1, 2, 3 atoms bonded to our central atom, and there are no lone pairs on our central atom. So these lone pairs on oxygen do not count. Only the lone pairs on the central atom make a difference in the shape. So on my table right here, here are my 3 atoms bonded to my central atom, 0 non-bonding pairs. My shape is trigonal planar. This is the 3D model of formaldehyde. So you can see that there is about a 120-degree angle here between the oxygen and the hydrogen, and both hydrogens here. So the double bond actually does not take up any more space than a single bond. Let's take a look at the Lewis structure of sulfur hexafluoride. Before we switch over to our VSEPR table, we need to remember that we have 6 atoms bonded to a central atom, and that the sulfur, the central atom, has 0 lone pairs. Here is 6 atoms bonded to the central atom, 0 lone pairs. The shape is called octahedral, and here is a picture of what it looks like. Here is our 3D model for sulfur hexafluoride. In our Lewis structure on paper, it really didn't look like we would be able to get 90 degrees between each of these chlorine atoms, did it? But you can see when we move to the 3D model that we actually do have 90 degrees between each of the chlorine atoms. Just like with methane, we can use wedges and dashes to make our Lewis structure look more like the 3D geometry. So I am going to add wedges to these 2 chlorine bonds to indicate that these 2 chlorine atoms are coming out of the page at you. I'm going to erase these 2 bonds and instead put in dashes to indicate that these 2 chlorine atoms are behind the page away from you, and the 2 chlorine atoms with the straight bonds are chlorine atoms that are still within the 2D page. While wedges and dashes do help us represent a 3D structure better on a 2D surface, nothing beats holding that model in your hands. The key to predicting the correct molecular geometry is obviously to make sure you have the correct Lewis structure. So make sure you're confident in your Lewis structure before you start predicting molecular geometry. Now, I also happen to find the molecular modeling kits very helpful. These are easy to find online, they're relatively inexpensive, and if you're artistically challenged like me, it's really helpful to have them to visualize what the molecules look like in 3D space. I hope you found this video helpful, and thanks so much for watching.